Organohalides, so compounds with halogens on them. We've already been talking about them, but we're going to talk about them explicitly now. So they're important in that they're used often as solvents. We've seen carbon tetrachloride, methylene chloride, 1,1-trichloroethane. They've been used as anesthetics like chloroform. Ethyl chloride is used to diagnose dead teeth. So you put a little of this on there. As it evaporates, it cools, and so you get a localized chilling effect. And if the tooth is alive, you can feel this. If you can't feel it, then you know your tooth is dead. Also pesticides, so DDT is a classic one. Don't use it so much anymore. It affected affected sodium ion channels in insects, so it fires their neurons, and so they spasm and they die. Vicane, you tent a building and you pump a bunch of Vicane in there. This stuff they use to kill termites. Vicane, you've got the formula there. Sulfonyl chloride, that doesn't make sense. Fluoride. So it releases fluoride, which affects fat storage and a variety of other things. Just interesting point. Speaking of pesticides, my dad, Ron Toyota, crashed his Piper Pawnee a few times. He used to spray crops out in Ontario. Fun fact, I guess. Refrigerants are also a really important use of organohalides. So R12, they relatively recently got rid of it. It was called Freon 12. It was destroying the ozone layer, some fool thing, so they stopped using it. Now we use, I think, HFC 134. Just not something we need to know, but they have a weird system of naming these things. So you'd say, in this case, the first number is the number of carbon atoms minus 1. The second number is the number of hydrogen atoms plus 1, and the number of fluorine atoms. So R12 is really R012. So number of carbon atoms minus 1. It's got 1 carbon, minus 1 means 0. Has no hydrogens, so 0 plus 1 is 1, and then there's 2 fluorine atoms. So they had this weird system, or they have this weird system for naming these things. Names that we should recognize, though, are these. So alkynyl halides. Put something on an alkynyl carbon. Vinyl halides. A vinyl, remember, is a carbon in a double bond. Aryl means attached to benzene. They're making all chlorides, right? But these could obviously be fluorides, chlorides, bromides, or iodides. Fluorine often behaves differently than the other 3 halogens. Alkyl halide, put your favorite halogen onto an alkane. Germinal, dang it. Geminal is what this is. Geminal means on the same carbon. So this is a geminal dichloride. Right? We can get that by adding 2 equivalents of HCl to an alkyne, right? Vicinal dihalides are when they're on adjacent carbons. We're using a bromide this time. How do we make this guy? Right? If we had the alkene, Br2, through the bromonium ion, we'd get anti-addition, wouldn't we? Right, so these are names that we should be able to recognize now. We've been naming these things, but let's go ahead and do these here. So let's name these. Probably what you should do is pause me, try to name them, and then see if we agree. 2, 3, 4, 5. Let's see, so looks like 2 chloro, 4, 2 bromo, chloro, and then 1, 3 pentadiene, going along. And we can see that it is the Z isomer, isn't it? 4 chloro, 1, 3 pentadiene. This guy is 1, 2, 3. Remember, the alkene gets priority in there. So it's going to be 3 chloro. And then we don't need to say 1. We can just say cyclohexene. And we can see there's a stereocenter here, so we need to assign this. So 1, 2, 3, 4 in the back, clockwise, R, 3 chlorocyclohexene. Here we've got this guy, the alcohol. So the longest continuous chain, it includes the alcohol. So 1, 2, 3, 4, 5. And I think we can name that. It's going to be 5-chloro, 2-pentanol. Agree? Finally, this guy. So again, longest continuous chain, including the alkyne. So 4, 5. All right. So we've got an ethyl at 3 and a bromo at 4. 4 bromo, 3 ethyl, pentyne, right? Or pent1-ine. I think that's it. And 1, 2, 3. H is in the front, clockwise. So S. 4-bromo-3 ethyl pentyne. This carbon's also chiral, but there's no wedge or dash, so we can't tell if it's R or S. All right, so we've been done doing a lot of naming, and keep all those rules in mind. Next, so briefly, the structure of alkyl halides. They're tetrahedral on carbon. Going down the periodic table, right, they get larger, don't they? So iodine is the biggest. Bromine, they exist as diatomics mostly, F2, right? Br2, Cl2, I2. They're more electronegative than C, so you've seen that. Their density's generally greater than water, but because of the chlorine atoms are pretty big. Boiling points are relatively low because of their size. So the boiling point of chloroform, this is 61 degrees. Methane is, well, much lower. Why is it so much lower? 2 reasons, right? First is this is a polar molecule, right? This is a non-polar molecule. So only London dispersion forces, right, holding these guys together, where these are dipole-dipole interactions. And this is a much bigger molecule too. So that's why his boiling point is so much higher than that of methane. If we were using it in an extraction, if I had water and I had methylene chloride, where would the methylene chloride go? Because his density is greater than water, he'd be in the bottom, water be on the top. If we put ether in there, right, he's less dense than water, he would be on the top. So it's really just the density that determines where it goes. Oh, nice. All right, so, whoops, wrong button. Come on, man. So synthesis of alkyl halides. We already know how to make them. So we know hydrohalogenation. We go through the Markovnikov intermediate, but we know we're going to make this guy, right? The mechanism we are able to draw. So the alkene's the nucleophile in the first step, right? You add the hydrogen, you get the more stable carbocation, right, which is the Markovnikov. Is the reason we get the Markovnikov product. Then that adds, and we're there. We saw with hydrohalogenation that sometimes we would get rearrangements, right? With this guy, you have a 1,2 methyl shift, don't you? So we get the secondary carbocation, do a 1,2 shift. Now we got the tertiary carbocation, and chloride adds. Right? These are all mechanisms we know. Halogenation, we know we make the vicinal dibromide, the anti, we get a pair of enantiomers, and we go through, hopefully you can see this, the bromonium ion, right? The reason we get anti-addition. HBr peroxides, so H2O2 or, well, that's all, peroxides. Remember, we get the anti-Markovnikov alkyl halide, and the reason for that is in the radical mechanism, bromine adds first, and you form the tertiary radical, which is more stable and faster formed than the primary in this case. So we already have some reactions of alkyl halides, and we know one way to synthesize alkenes or to react alkyl halides to make stuff. So dehydrohalogenation, right? We look for adjacent hydrogens, the so-called beta hydrogens. Hydroxide's a strong base, grabs the proton, electrons go there, falls over, and we get our elimination product, right? Plus bromide, plus K, plus, and we know that gives us the Zaitsev product, right, if possible. Right, I could go this way, or I could go this way. The more substituted alkene is the more stable and the one that is formed fastest, right? We're going to talk more about ways to make alkyl halides, some more radical reactions.